Hey guys, thanks for tuning in. Just before the episode starts, I'll give you a little description about it. I'm with my mate Josh, and basically he's really into science and stuff. I do kind of explain this in the episode, but just briefly, We want to start a series where we just talk about sort of sciencey things that I don't understand, and just kind of explain them more in a simple way, so morons like me can understand them, and yeah, just kind of have a chat about it. So it's like a nice longer conversation. I ask a few questions and Josh answers them all very well. I think we just talk about its energy, like how light bulbs work themselves, like how power plants kind of generate heat, how things like have energy within them a little bit. Yeah, conversions, that sort of thing. It goes together very smoothly. It's a really good one. And my favourite part is when we talk about how when you push a table, you're not actually pushing a table. It's actually just the transference of energy, and the reaction of it is causing it to move. And that sounds really weird, but it's so cool. And when he first told me about it, it blew my mind. So yeah, we go into detail about all that sort of stuff. And yeah, it's a cool podcast. So we'll be doing more like this in the future. We haven't figured out what we're going to do about it yet, but there's going to be, standard sort of things. If you have any recommendations, let us know. Put on Facebook or YouTube or anything like that, and we'll cover it, I guess, Yeah, well, thanks, guys. See you later. Welcome to Genuine Chit-Chat, where we have honest conversations with interesting people. And I'm your host, Mike Burton. Hey guys, welcome to another episode of Genuine Chit-Chat, where we have honest conversations with interesting people. And today's interesting person is Josh.
Hello.
And yeah, basically me and Josh have decided we're going to kind of do this little series. I mean, Josh is probably going to appear on other podcasts, potentially with other people, and talk about other stuff. But we're going to have a little series of podcasts, which is going to be called Science, but Simple. So it's just like the kind of idea came from it, basically where Josh is really intelligent and is really into science and stuff, and I like to consider myself a fairly intelligent guy, but when it comes down to it, I really don't know a lot of the basics of just standard science that people know. Like the other day, well, it was a couple of months ago now, I think, I was just sat in the lounge and I was talking to Josh, and I said I didn't know how light bulbs worked, and I just didn't understand, and he just told me, and we spent about 45 minutes talking about it, and so I thought, well, that can be a good first episode. We'll probably talk about the human body and stuff. I mean, one of your specialities, like what have you studied, Josh?
Well, been the general stuff like the GCSEs and things, did all three sciences individually. Then I moved on and did biology, chemistry, and environmental studies as A levels with maths as well. And then I've gone on and done a marine biology degree. So on the date of when we're recording this, last summer, which would be July of 2016, I don't know why I had to think about that.
You want to be the scientist, the good one. I couldn't think about a year ago.
But that's when I graduated with my 2-1 masters, so everything's gone okay. I'm just looking at going into teaching from now on. Probably still have a specialisation in biology to some degree, but teaching in secondary school is going to involve most sciences anyway, and I have to at least that level, a decent background in all three. Physics probably being the weakest, but biology and chemistry are definitely there, so.
Yeah, well, this can be like a tester for your teaching. Like, you're going to be teaching like loads of like teenage kids who like some of them want to know about it and some of them don't want to know. And to test, so before that, the precursor is testing me, who should have been taught all this sort of stuff, but I went to a Catholic primary school and they didn't focus on science that much, especially not the planets. Like this day, I still can't name all the planets like really quick, like most people can, in size. And there's that rhyme where you can say it in the right order and it shows.
Yeah, I don't know the pseudonyms, whatever they're called.
Yeah,
is it pseudonyms?
Well, pseudonyms is like another word for something.
It's not.
Like the rhymes and stuff for it.
Yeah,
I know what you mean. Acronyms or whatever. The acronyms to make you remember it and things like that. But no, it's like there's certain things where I didn't know that in primary school that much, and then in secondary school I did it a bit, years 7 to 9, but then in year 10, 11, in England, I think it's changed a bit now. I don't think you really get as much of a choice, but basically you could choose 3 things. It was applied science, triple science, or core. And core and triple almost the same thing, as just core was just slightly less. It was just you got 2 GCSEs for core, triple you got 3. Core, triple especially, like each GCSE was a specific subject in science, biology, chemistry, and physics. And then I did applied because I said to my teacher, she was like, "Do you like exams much?" And I obviously as a young teenager, was like, no. And so she was like, why don't you do applied? It's pretty much all coursework. I was like, okay, that sounds fun. It was not fun. It was so boring, it put me off science for absolutely bloody ages. And I know quite a few people we know, like our friend Jasmine. She said a lot of the time in school, or some other time, she was like in science class or anything like that, and she would just be kind of bored, and it wasn't grabbing her. But then she's come out, and she's listened to the occasional podcast about it. She watches videos on it and documentaries. She's really into documentaries, especially things like Brian Cox and things like that. And it's just like, because she's now developed this love for science. And it's kind of happened with me as well, and a couple of other people, like Reese, he said the same thing. It was just like, and what what I want to kind of do is, I'm really interested in knowing all this sort of stuff now. I listen to a lot of podcasts with like physicists, like, you know, Neil deGrasse Tyson, that sort of thing. And I watch, you know, obviously David Attenborough documentaries. They're quite low level knowledge of, you know, how much it comes down to the core science of it. But it's just like, there's so much I want to know now. And whenever I talk about these sorts of things, you always know what to say. So yeah, this is science, but simple. And the first one, this one's going to be called a light bulb. Basically, how does energy work? Do you want to say anything before we start, George?
Yeah, from what you said, I think for the most part, the GCSE system for the sciences still works the same. I'm not sure whether it's just split into the 3 individuals now with the new GCSE system that's just started.
Yeah.
But definitely I can understand the whole thing. Like, for me personally, it's that interest in the science aspect of things and understanding those things has always been there, whereas some people have been put off by their experience sometimes at school. And I think that's a lot of the problems that not to get really deep into this for this particular one, but like our school system at the moment doesn't hugely encourage people to be very like interested and engaged and like actively going out and looking and learning for themselves in particular subject areas. So
Yeah, I agree.
It ends up like, now I'm going to be talking about things to do with energy and general like light bulbs, trying to keep it to like the kind of everyday stuff that everyone knows.
Yeah.
But then go into like how that sort of stuff works and the fundamentals and behind that and the science behind it, because it's stuff that everyone sees every day but doesn't think about, and you go into it and potentially get people interested in some science of it as well.
Yeah, I mean, what, just as a little preview thing, if people do know about energy and they listen to this for a little bit and they think, oh, I don't need to listen to this anymore. Have you thought of any sort of ideas of some future ones? Because I think we've spoken a bit about. I'm interested in that the human body quite a bit, like how blood works. Because you and I think Reese were telling me about like how blood cells actually transfer oxygen around the body.
Oh yeah,
and that's how it makes things work. And I literally didn't know that at all.
Mm-hmm. I know a lot of that sort of thing can be like crossover and fundamentals of biology. For me personally, doing a marine biology degree, and that my interest has always much been more on the animal side of things and like other things that basically not human, because I don't like people.
We could have like, you know, we're gonna try and have these to be about an hour long each, and they're gonna be released quite sporadically. I don't think there's gonna be a necessary plan. We could probably try and do it monthly. It probably wouldn't be that hard to do, just, you know, every now and then.
Yeah, definitely. You can talk about some things like ecosystems and maybe some things to do with like how agricultural systems.
We can talk about your favourite animals and stuff.
Everything, yeah.
We can have a little bonus episode. Just
field courses I've done and things, so it could be interesting things to talk about at a later time. But
it's like it can always be things like, you know, we just have one little cheeky one where we have we talk about our 3 favourite animals or something and why, and I'll obviously have to do a little bit of research on the animals as well, because one of my favourites is like panda, for example. I really like them, but you look into it, pandas, like for example, they terrible breeding. They're like,
oh yeah, they don't like sex.
Yeah, it's quite funny, and it's just things like that. Like I'd like a little tidbits and stuff.
You give them the opportunity to reproduce easily, and they just say no.
Yeah. But it's like so, and we can have these little there'll be topics that are more specified, like this one will be a bit more linear, but then there'll be other ones which are just a bit more free, you know, but it's just science but simple. It's just easy to digest sort of knowledge in a way. It's like every part of this podcast, I just want to kind of talk about everything really that interests me and anyone's passionate about, and I'm getting into science more, and you're very passionate about this sort of thing, so I'm pleased to have you on, mate.
Well, let's get started and see how this goes, because this is a new experience for me as well. So well, not so much for you now, but
well, yeah, this is my. I'm going to start releasing them in different orders and stuff that I've actually been saying. So now I think this is the 8th I think that I've done 8th guest.
At least in order of recording.
Yeah, seventh or 8th person that I've had on, and a lot of the podcasts have been split into 2, or will be split into 2. But the order that I'm doing it, this may not come out till the 12th person or something, or may come out in a couple of weeks. You know, I haven't.
Yeah.
Certain people's conversations aren't like specific to time, so and some ones are, like Callum and the band and stuff. You know, that needs to be released relatively soon to when he's talking about his band. It needs to be relevant, and you know, in terms of the conversations go to. But right, so the big question, the easy is actually probably the hardest question almost is. So how does a light bulb work? So, you know, everyone knows standard light bulb, you know, it's made of glass, you screw it into the socket, whatever, you flick the plasticky looking switch on the wall, and then somehow, this is the thing that always baffled me, somehow, like, since caveman times you could do this, like, there's the amount of stuff that's on the planet right now, there's always been on this planet. So if you went back to caveman times, you had the know-how to do it, and somehow the manpower, you could create electricity, and you could create, like, in theory, iPads when like, the dinosaurs were about. If we take out meteorites contributing to something to the equation of that, but if we just say you could create iPads, but it's like you put bits of metal together and do certain things to them, and then you have from this just metal something that produces not only light but also heat, and light is such a weird fucking thing. You know, it's so strange, and it's just. It's madness to me. It's always just been crazy that you can, like, obviously iPads and all that sort of stuff is impressive, but just to the baseline first thing of just creating light, that was the start of all. Obviously the wheel was the proper start, but like the start of true civilization, almost emphasis on the civil, was when we could have these houses that obviously we had light in that weren't made from like fire and stuff, and then shortly after that electricity became a thing, and then the whole technological revolution, that's where it began. It just started, it went so fast, like Victorian era and stuff, when we had lamps and stuff, it was quite slow moving, and once light bulbs came out, and electricity specifically, it just changed everything. So yeah, how does it all work then? Where should we start?
Okay. The first thing to understand is that obviously electricity isn't something that as humans we created. It's always been in nature.
Yeah.
But a lot of the times in natural environments, it's simply just build up of large amounts of static electricity. So, for example, in your thunderstorms and lightning storms, that is just a lot of water in the clouds, like condensed into the clouds, just moving around, rubbing against each other, creating a lot of static electricity. It builds up and then discharges in one big go.
Okay.
What we're talking about with light bulbs is an electrical current, which is, as far as I'm aware, much more of a man-made thing and a controlled form of it, where through the wiring and the filament of the bulb and the wires in the walls and the power cables and everything is simply just through the metal. Metals form what is called a lattice in their molecular structure, but I'm not going to go into massive detail about that. But what it basically means is that the electrons, if they're given a push, have the freedom to move across the atoms and between them and be passed on.
And with that, for more visual idea of it, this is when you've got the atom and you've got people visualize it as there's a circle that's like filled in, and that's the center, and then you've got the rings almost around it.
Yeah, and the electrons are the things whizzing around the outside.
Yeah, so it's like, you look at it, it's a circle that's filled in, and then loads of rings around it coming out, and each ring has a certain amount of electrons on it, did you say?
Yeah.
And so what happens is, if the atoms are close enough together, those rings, is it where the rings basically overlap, and then the things can...
It's not so much a spacing thing, it's just that because of the way that a metal forms in its solid form...
Yeah.
It allows those electrons to move between them, and be transferred if they're given the push to do so.
I see.
So what we are talking about, electricity is much more of technically like a layman's term almost. What we're actually talking about is electrical potential energy,
right,
which is basically you're wanting to produce one relatively positive end,
right,
and one relatively negative end. And then the electrons will flow from the negative end, where they're in high concentration, to the positive end, because electrons are negatively charged. And in that movement, they can then pass on their energy to things, and that transfer, which is what happens. When you have a very thin wire, that just means that there's a lot less like space for that transfer to happen through. And that then creates what's called resistance.
Right.
And it's that resistance that means that, say, wiring heats up and then starts to generate light in the case of light bulbs.
So it's these electrons moving about are obviously a way of thinking about it in almost a really physical, practical way. It's almost like if you look at people running through somewhere and they're rubbing against the walls and stuff, the friction of it, it can even cause heat. You rub your hands together, it makes heat, and that sort of general, like really simplistic idea of it is, you've got this, and they go from minus to positive. They go from negative to positive. That's correct.
As I think I always get very confused about the particular direction, because when you're talking about like circuits and batteries, you always say that the circuit flows, and by convention the circuit flows in like the positive direction, but the electrons actually move in the other way. So it's weird, and I don't quite get that.
Okay.
The circuits is not like exactly my strongest point, but in terms of the energy side that we're looking at, this is I can do that.
Yeah, that's fine.
The thing about the light bulbs though is that with anything like with heat, obviously you're going to end up potentially with combustion.
Yeah.
And that is functionally what the element in a light bulb is going to be trying to do. It's going to be trying to combust. To be put quite simply, a light bulb will not work if there is oxygen inside the light bulb, because the filament will burn instead of glow. So I think most of the time, light bulbs are actually filled with noble gases. I think argon mostly it's used.
Okay, I have no idea.
So I think because you end up with like neon lights and stuff, that's another thing that's to do with the colours and glowing and stuff. But again, that's a noble gas. Noble gas is basically just really unreactive. They don't do anything. But to fill it with a noble gas that's not going to do anything and then keep oxygen out, that's basically how they make sure that filament doesn't start burning.
I see. So you've got me coughing grossly. So you've got this, basically the filament, it won't get hot because it won't combust. So it won't damage itself by getting too hot, because it won't be able to have oxygen to be able to actually almost ignite it. It's got almost heat potential energy, and it's just like, if oxygen gets near it, that'll combust, and that will be what damages the filament.
Yeah, like combustion is basically just a reaction in which oxygen reacts with something as it burns.
And that's when a light bulb breaks, the light always goes out.
I don't think the heat itself, heating up, is going to be doing something to the filament, because otherwise like the light bulb wouldn't just blow randomly anyway. Light bulbs will just last indefinitely.
Yeah.
But in terms of if oxygen got into a bulb, it would just go straight away. Like there'd be no chance of it surviving. But again, this is the whole idea, is this is your electricity running through the wires into the bulb, all that, the heat build up, which is making what makes the metal glow. Like when you see a furnace from like a smith or something, you see all the molten iron or whatever they're making something out of, and it's glowing with heat.
Yeah.
It's just another form of energy release. So as, say, this energy is being transferred from the electricity into the wire, that is producing the heat energy through the resistance and then releasing that also as light. So it's just a conversion of that electrical potential energy into thermal and light energy.
So you're saying it's the resistance that's causing the light itself, or like what?
It's like almost like a chain reaction of like the resistance is what causes the energy to be built up in the wire, essentially. So the reason why the wire to the light isn't hot and glowing, and the one inside the bulb is because the wire that's inside the bulb is very much thinner, producing a lot more resistance. Right. So you have the same amount going through a smaller space.
Right.
And that produces that like resistance and the heat
and it's
and
the
light
resistance
and
itself that's
the
causing.
heat and the light is basically just a discharge of the excess energy.
I see. Okay. Yeah. So there's all these, to put another human way of thinking about it, because I like analogies and I'm terrible at them. It's just like loads of people kind of running like through a corridor, and then it gets really, really, really thin.
Yeah, and you're trying to fit the same amount of people through through a smaller space,
and they somehow manage to get the same amount of people that amount in, but it obviously causes so much friction and stuff. It creates the light and whatnot, and obviously then when they kind of go round the corridor, almost round in like a U-turn, it's almost like them going round the bulb, and then when they come out the bulb, they come out the tight corridor, they can do the open one, and then everyone can kind of run, not rubbing against each other, sort of thing.
Friction is a good way of putting it, because friction itself is almost just a transfer of energy. If you've got something moving fast, and you apply friction to it, it starts to slow down because you're changing that kinetic energy, that's the energy of the movement, into, say, if you're slowing something down and it heats up, you got thermal energy coming out. You might have sound energy coming out, which is essentially just, again, sound energy in itself is almost like kinetic energy anyway. It's just like in the air or things, like molecules bumping into each other to transfer that sound across.
Yeah. So what briefly explain the thing that blew my mind, which just shows how much a simple man I am. And this is only like a month or two ago, so it's not even like I was young or anything. With energy, right? The thing that got me was the whole, when you push something, you're not actually pushing it, sort of thing. Do you know what I mean? Where it's the transfer of energy. That's basically how it works.
Oh, right, okay, yeah.
So when you push a table, you're transferring kinetic energy.
Yes.
So explain that in a way. Like, explain that sort of thing.
Right, I'm trying to think how I explained this at the time. Basically, to put it rightly, when you're, say, pushing something, say the extension of your arm, that is a chain of energy conversions from the chemical energy stored within the reactions and the things in your body into the kinetic energy for movement, and then you're basically transferring that kinetic energy then into something else to move it.
So when you're pushing something, you're not in a way actually pushing it. You're putting an amount of energy into it in a certain direction, and that transfer wears you out that amount of energy, because that amount of energy comes out of you and goes into this thing.
Yeah.
And that energy that goes into it is the thing that makes it move.
Yeah, which is essentially force.
Yeah. So when I push something, I'm not actually pushing it. I'm transferring my kinetic energy into it, and the reaction of that is that it moves forward. When you told me that, I was just like, are you fucking serious? I was like, what? Because I've always known the thing of that, because atoms are actually, there's more space between them.
Yeah, that like 99% of an atom is empty space.
Yeah, so that includes us. It's one of those things where it's like the infinity sort of idea, where you can go into like smaller and smaller in infinite amount of times. It's like you say there's a measurable. If you say, okay, how big is something? Well, it's between 0 and 100 something. Like say 100 meters. So between 0 and 100 meters, you can go, okay, well that's finite then. This can only be that big. It's like, no, not really, because it can actually be infinite. Because if you go to between the space, the amount of numbers between 0 and just 1, the numbers between that, when you go into a small enough decimal point, is infinite. And that's how small you can go, and that's infinite. And then it's like, if you go far enough deep down into what actually makes everything, it's actually more space than anything. It's like there's barely any of it.
Yeah.
It's like you go so far down to the infinite minuscule.
Even though this table is solid, and you are solid, and I am solid, technically most of what we are is just empty space.
Well, that's why there was that scientist guy, wasn't there, who once said he had this thought experiment, and he said every morning he just walked fairly fast into his wall, because he said, in his mind, theoretically, you should be able to walk through walls because you're less dense than the wall. He said that's in theory, and he obviously just did that every day, and people thought he was a bit mad, but
that does seem a bit strange.
Yeah, you do it once, twice, you think you're probably going to stop doing it, mate. It's not good for you. Oh well. But yeah, so got the general idea of the kinetic energy and so just to reiterate, the electric energy is just the way I imagine it at least is loads of people running through somewhere, and then when it becomes a thinner wire, then those people at the same speed and the same amount of people go through a tinier space. That causes friction, which is what is actually what's causing the sort of the heat and the light in a way. So that's step one. And the filament is it the metal in the filament is
where basically the energy is being discharged from.
I'm saying is what makes the filament and the wire, what makes them bigger or smaller? Is it the actual literal physical size of it, or is it? So it's literally that simple. Okay, cool. That was easy, not easy. Coughing really loud.
Like it's quite literally the idea that the wire is thinner. Like, I think a lot of filaments sometimes in light bulbs look slightly thicker because they're actually almost like coiled.
Right.
Which is why sometimes basic drawings of a light bulb sometimes show that filament being like a coil, but that sometimes they're just like the straight wire and things. I'm not entirely sure what goes on with the light bulbs that like the U bends and stuff through them.
They're the energy efficient ones.
Yeah, I'm not quite entirely sure whether they have a filament or anything inside them, or they work much more like neon lights and stuff.
Yeah.
But this is like your kind of standard
when
incandescent bulb.
When
like,
someone has like an idea in a cartoon, you get the one
that style of light bulb. This is definitely how they work.
Yeah. That's cool.
In terms of the actually like moving back, we like move back through the system to like, well, okay, so we're saying that energy. Well, let's go to fundamental laws of thermodynamics and use some big words.
Yep.
Basically, energy / matter cannot be created or destroyed, only transferred from one form to another. So that electrical energy, we have energy, it's being discharged, that's an energy transfer, but then what's generating that electrical potential energy? Where is that energy coming from? So you trace that back basically through all the power lines, everything back to your power stations.
Right.
And essentially what's going on at the power stations, and I think it's pretty much, even to the extent of nuclear power stations, which do work on a slightly different system, but still, what you're essentially doing is heating up water, turning it into high pressure steam, and letting that high pressure steam force a turbine to turn. And that turbine will more than likely be attached to a giant magnet, and then there'll be a wiring coiled around that magnet, and then that magnet just spins and turns. And because of the positive and negative side of the magnet, that basically pushes the electrons around the wire, and that's what generates the current.
So the magnets are what make the conversion of it more. It kind of pushes it forward more in a way.
Yeah, that in itself is just like a chain of like 3 different energy changes, because you have whatever your fuel is, whether you're burning coal or using nuclear, or you've got a wind turbine doing the same. That's essentially in terms of the water, at least, when we're looking at coal and nuclear and...
if you just explain burning, like the wood example is the easiest for me to understand.
Okay.
If you just said just basic fossil fuels, you have these things, wood, they have energy in it, and explain...
And so that, when we're looking at that, is chemical energy, and that's essentially the...
Same as when you eat something as well, like chemical energy. Just to clarify for people.
It's essentially just the energy that's stored within essentially the bonds of the molecules in that whatever compounds that is.
Yeah.
Most in terms of coal, we're looking at like carbon compounds, hydrocarbons, which are basically made up of hydrogen and carbon.
Yeah.
Can be a mix of them, different things. You've got methane, ethane, propane, butane, goes on and on. Then you get the solid ones much later down the line. A lot of them are like gaseous, then liquid, and.
So, and you said to me when you, if we use this quite the base easy example with fire, you heat it when you're heating the coals, and what you're doing is you're causing a reaction to change the chemical energy into a different kind of energy.
So this is where I'm going to mention a word called enthalpy. And enthalpy is essentially the energy change within a system.
Right.
What you're looking at is essentially you have your lump of coal, say, or lump of wood or whatever, and you have to. It doesn't just spontaneously combust.
No.
You need to put energy into it first, start burning.
Right.
But as you can probably tell a lot of times when you had a fire, it's more difficult to get a fire to start than it is for a fire to keep going.
Yeah.
And that's essentially what we call within like chemistry, the activation energy. And say so, I'm going to use my hands and try not to hit the microphone. We have your energy within the coal or wood here.
At the top, okay, yeah.
That's more the middle, but yes.
It's very hard when you've only got one hand up.
Yeah. And then you have to put energy into it to start that reaction, and once that reaction started, the energy that you've put into it discharges. Oh, I've hit the mic. And then the rest of the energy is that reaction between the carbon and the oxygen in the combustion reaction also releases more energy. So then the energy within the molecule, so for example your basic equation of carbon plus oxygen to carbon dioxide, you have less energy contained within the bonds of the carbon dioxide than you do within the bonds of the carbon and the bonds of the oxygen.
So the conversion makes them lose a certain amount of the energy.
And that is what's discharged as the heat and the light that the fire generates.
So to make this, because that sounds quite confusing, it may sound quite confusing to a lot of people, so it's actually quite a simple way of thinking about it. All you're doing is making these two things, you're just converting them, almost just literally converting them into this other thing, and in doing so, a certain amount of energy is discharged.
Yeah.
In this instance, the energy that is discharged is fire. Is that correct? Like the heat energy.
Fire is basically the what we see as the reaction happening.
Yeah.
The energy that's coming off is the heat that we feel, and the light, which is obviously then what we're seeing.
Yeah.
And to put it really basically, is basically you got your carbon and your oxygen.
Yep.
And the carbon is bonded to carbon, and the oxygen is bonded to oxygen.
Yep.
You put in energy and break all of those bonds, and then they recombine as something else.
Yep.
And the energy that you put in to break those bonds is less than the energy that is given out when those bonds reform.
So when I see, so it's almost like, yeah, I could almost describe it, you push something a certain amount, and then it pushes something twice as hard. It's kind of like that in a way. You put in a certain amount of energy, and a certain amount of energy comes out because that's the reaction. That's what happens. And all the energy, this is the thing that blew me away of how kind of simple it is in a way, when it's kind of not simple, obviously, when you go into the details. But all electricity is, and energy, and all this sort of stuff, every single thing is either the reaction happening of conversion, of just changing one type of energy to another type of energy, or is that type, the thing that comes off that type of energy. So it's literally just, okay, you convert this type of energy into this type of energy, and also this type of energy comes out. It's pretty much that simple for almost everything. It's like, for when it comes to the, like, with electricity, when you get down to the baseline, it's just, and when you make fires and stuff, it's just, literally you're converting these things into this thing, and it becomes this thing, but also as a side effect, this stuff comes out.
Yeah.
It's just like,
which is a lot of the time where you end up getting some, say, waste energy as well. So if you're burning coal in a coal power plant, that, regardless of what you try and do, that fire is going to be producing light, but you want the heat. So the light energy that's produced by the coal is, when it's burning, is not useful to you.
Yeah.
But the heat is.
Yeah.
And that's just the way things go.
Yeah, there's nothing you can do. You can't make
energy.
it have less light to make it have more heat. It's just the amount of heat you get a certain amount of light as well. Yeah. And obviously the best way to do things is to try and make a conversion where as a highest amount of percentage of energy is the stuff that you want. Yeah. Yeah.
The next step is basically where you're converting, essentially the useful energy in that reaction is the thermal energy or the heat energy, and you're wanting to transfer that into the water and get it into high pressure steam. When that high pressure steam then is jetted out onto the turbine, that's basically that heat being converted into the kinetic energy of the moving of the turbine, and in turn that moving of the turbine and the magnet, which pushes the electrons on, converts that kinetic energy into the electrical potential energy, where it's moving those electrons through the wiring.
Yep. So it's literally just, you get fossil fuels, you make a reaction happen, and it creates heat energy, and that goes into the water, and then the heat energy makes the water, it sprays and that sort of thing. It makes the jets, it makes it move, it pushes out, and then when it uses kinetic energy, it turns the heat energy to kinetic energy and hitting the turbine, and then the turbine has now had the kinetic energy put into it, so it's also moving, and then with the use of the magnets, it converts it into electrical energy. So it's just everything with energy, it just traces back to, we didn't create it from nowhere. It kind of seems like you did, but it's just
going from one form to another form to another form to another form.
And
of course that coal itself is just basically the energy stored from something that died millions and millions of years ago. And it's just like sat there. Just a chemical store of energy in the atoms that's there. Much like it's almost like a natural battery, and obviously that it runs out, so it runs dry.
So with the light bulb thing, just to clarify, what happens is you get it's pretty simple. You can think of it. The most basic way of thinking about it is not fully correct, but it's literally just like it's almost as simple as you basically burn something, it makes fire, the fire heats up water, the water moves the turbine with a magnet makes electricity, and then they send it basically through a wire to your house. Now the switch is the middle part that we're missing out, okay? Is just so we understand how once we flick the switch and the electricity that's obviously been converted from all that time away, all that far back, it gets the energy is there. You flick the switch and then it lets the electricity run down the wires, get into the light bulb, and then obviously goes into the thin corridor analogy, creating light and heat, and then goes back down. Blah blah blah. Okay, so when you flick the light switch, just standard on and off light switches, I'm not getting to any of the other ones at the moment. When you flick them, obviously I know a general idea of what a circuit is, but if you just explain what a circuit is, like what that's doing, like where's the electricity in our houses going to
basically
a point?
To allow the electricity to flow,
you
need a complete circuit, and that's why everything the light bulb goes into the light bulb through the filament and then back out again, and through the wire back through your live, your earth wires, all that sort of thing. Essentially what the switch does is tell you whether that circuit is complete or not complete. It's quite simply, are we connecting up or are we not connecting up?
A really easy way for people to visualize this, if they can't remember for school, is basically just have a square at the moment, and then one of the lines where the square is, it's almost like you just... Ow, I just hit the mic because I'm being more on using my hands to try and explain things on the podcast. It's almost
I thought
like
it would be me that's doing that more.
It's almost just like a door opening. It's just like something doesn't. It's just no longer connected. It's that simple. And so,
or like when you have, say, you've got a train going from A to B, and you've got a junction on the way, and the junction's going to point C.
Yeah.
Point C doesn't go anywhere. It's just a dead end.
Yeah.
So you need to switch it over to track AB, and then the train can flow through.
Yeah.
And that's literally all you're doing, saying, this can go through or this can't go through.
So the question is, when the light switch is off, does the electricity just go up to the light switch and it all just stops, and it's almost like a backlog of electrical current all the way back to the source, or what?
I'm not 100% certain. From my understanding is that obviously it's not going to flow anywhere if it doesn't have the complete circuit. And as I said before, it's not a case of energy will run up to something and then stop. It has to have that flow and transfer of an electron to place to place to place to place, like almost the way I know you'll know, but for anyone that doesn't, Newton's cradle, where you have the little things that bump into each other, knock the other.
You get them in like 90s films in an offices.
Yeah.
You get like 5 marbles on bits of string.
Yeah,
you
lift
pull one,
up.
it swings, go.
Yeah,
hits. Yeah.
The electrons will essentially run almost like that, but in one direction.
Yeah.
So it's like a tink, tink, tink. So in terms of the electrons, as far as I'm aware, the electrons themselves aren't moving very fast. But because of that like chain reaction, the transfer of energy and the movement of one electron from when it's instigated is actually almost instantaneous.
Yeah.
But so you don't have like energy like building up behind something if the light switch is turned off.
Yeah.
It's just not flowing through there, it's flowing to somewhere else, and there's other circuits in the house flowing through it. It's just not going to that route.
Yeah, it's like once you flick the switch off, it's not the flow stops and is there, it's the flow just isn't going that direction anymore.
Yeah.
It's almost like it backtracks to the last point that it could go in another direction, it just does.
Yeah, like if you remember at school series circuits.
Yeah.
And how if you had a parallel circuit, you'd have now I'm thinking of something else now. Ignore me. Let's scratch that.
We won't go into school circuitry then.
No.
But yeah, so with the light switch, so got the light switch, the light bulb, that sort of thing. That makes perfect sense to me, and that's a general sort of idea of thermodynamics.
Yeah, the first law, I think it's first. There's 3. I don't know which one is technically first, but one of them at least is that energy and matter cannot be created or destroyed, only transferred from one form to another.
Yeah.
Mm-hmm.
Yeah, that's I've got a few interesting spiritual ideas about that sort of thing as well, but I'm not going to go into them on a science podcast.
Yeah. When I went into the word that I said earlier as well, enthalpy.
Uh-huh.
Enthalpy is essentially the word that is used in chemistry for the change of energy.
Right.
So, for example, when we're talking about the carbon and oxygen combusting and turning into carbon dioxide,
Mm-hmm.
there's an enthalpy change between the carbon and oxygen and the carbon dioxide. And it's a negative one because the energy within the molecules themselves, the chemically stored energy, is less than it was before.
Yeah, so doing that, it basically took some of it. You've got, is it really simply almost like oxygen and carbon? So my throat is going. They've each got, for real baseline, this is based on nothing, 5 of energy each.
Mm-hmm.
And then you do the conversion, and the finished thing doesn't have 10, it has like 8. Because 2 of them, during the conversion process, went elsewhere.
Yeah.
And that's what you're saying entropy is.
Yeah.
Entropy.
Enthalpy. Entropy is something else.
Oh, God.
Might mention that a little bit.
Enthalpy.
Enthalpy, yeah.
Enthalpy, okay, right. So
Terrible for people with lisps.
Yeah, I can imagine so. Yeah.
Not quite as bad as some geology terms, though.
Oh, yeah.
Well, there's one in geology, I just mentioned it briefly, but it's great because it's basically, if you didn't want a lisp, you do have it now.
Right.
Batholith.
Batholith.
Granite batholith.
Batholith. So it sounds like someone's saying basilisk with a...
Yeah,
with
it's just like, okay, if you wanted to see what it would be like to have a lisp, there you go.
Wow. Right, so we're at the sort of 40-minute mark now. There's... I could either cut it now, keep it short, or is there anything else you'd like to add about generally energy and that sort of...
I was seeing as you mistakenly, but still mentioned it. I know I mentioned to you a bit before we not recording or anything, but entropy is almost the opposite of enthalpy. It's the energy that's outside of the molecules. It's like the like nebulous energy in the environment.
Right.
Whenever you're talking about enthalpy and entropy in actual terms, you're always looking at isolated and closed systems in terms of the like numbers and stuff and calculations involved. Realistically, that's basically impossible. But for the actual like concept's sake, I'd say that we're looking at an isolated closed system.
Okay.
Basically, entropy is like my favorite thing in chemistry because, to put it quite simply, it dictates that the world will tend towards disorder and chaos, but in an organized way.
Right.
So the way that it works is that if you have enthalpy generally, because you do have endothermic and exothermic reactions, so reactions that take in and release heat. So if you had an endothermic reaction, you'd expect that the environment around it to get colder. They're not hugely common, and a lot of the things you'll come across will be exothermic reactions that generate energy into the environment around the reactants.
Is that like volcanoes?
That's a load of geological processes and things that this is not quite relevant to now.
Okay, we'll go into that. Okay.
But so for example, your fire is burning, it's releasing energy, it's exothermic, it's based quite simply from the Latin of it, it's like out heat.
Yeah, it gives out.
So it's
heat.
giving out heat. But the entropy, when enthalpy would be decreasing and the energy within the molecules is getting lower, the energy in the environment is increasing.
Yeah.
So you have an entropy increase, and that's what it wants. It basically, almost the way that the universe will want to reach a uniform, stable state. And it will get that by having everything evenly spread, evenly mixed. Everything's all good.
Balanced.
Not like hugely organized, but everything is essentially like randomly mixed and done. So this is not an excuse not to tidy your bedroom, but there we go. So the idea is it almost like diffusion and things like that, where things will go from an area of high concentration to an area of low concentration. The same applies to energy and entropy. The energy is concentrated around the source, but will move outwards from it.
Right.
Until it wants to spread in a uniform way, which is why I say your radiator's heating the room, but the processes from that energy will make sure that eventually that heat is spread evenly around the room.
Yeah, if you leave it for long enough, then it will equal itself out.
That's essentially what entropy wants to do. And so you maximize your entropy as things become less and less differentiated. And when you have releases of energy, and that energy then gets transported around and mixed and everything becomes much more even, that is what entropy increases do and how that wants to react. So you're looking at enthalpy, which is the energy within the molecules, and the entropy, which is what's outside of the molecules. We're still looking at a closed system.
Yeah, that makes sense. Here's a question then that you may not know the answer to, and if so, I'm sorry for putting you in this position.
Try me.
Why is it then that you get, with a light bulb, you get heat energy come out of it, right? In theory, well, I don't know, what do we have with a light bulb? Why is it that, okay, light bulbs, do they get hotter? Obviously, light bulbs do get hotter.
Yeah, they do get hot.
But they don't radiate very much, do they?
No. Comparatively, the energy is very small.
Yeah.
As well as you're looking at the idea of like the actual conduction of the energy as well. Different things conduct energy in different ways and not as well.
Yeah.
You also have to look at something, especially when you're essentially, that is a direct energy transfer. Whereas you're from one form to another, which has its problems with efficiency and everything like that. When you are looking at your radiator, or you're not having any reaction there, you're just having, okay, the thermal energy that's been stored within the water is then being transferred to the radiator, the metal of the radiator, and then into the air.
Yeah, so
it's just heat being moved from one place to another, rather than one type of energy being converted.
So to clarify with the radiator ease of it, it's just water, which is hot. It's got, and the hot is the heat energy, and it's going up and down all these metal tubings, and like the person in the like the people in the corridor, it's rushing through there, and it's, while it's basically in a way of thinking of it causing friction on the inside of the metal tubes, it's making the heat energy come out of it.
Not even that complicated. It's
even
literally just, oh look, this water's hot, and the radiator at the moment is cold. So the heat moves from where it's hot to where it's cold. Much like your cup of coffee or tea cools down if you leave it out on the side. Or, to put it even more bluntly, when you first make that cup of tea, it heats up the mug, and that mug becomes hot to touch. So you want to use the handle.
Yeah. You just want to talk about tea all the time, don't you?
Yeah. So it's like the whole resistance thing is more exclusive to the electrical current thing and producing the heat and the light from that. In terms of radiator heating up the room, that's literally just, oh look, this place is hot, this place is cold. Heat will move to where there isn't heat.
But why does light not do that?
Light does.
But it gets blocked in a different way. Obviously, light is a different kind.
Light
doesn't. What I was going to say is, why is it that if I have a light bulb on, it'll get hotter and hotter, but it won't. It does get brighter to a degree, but why is it doesn't just keep getting more and more bright as it gets hotter and hotter? Why is it not like an infinite brightness?
That's to do with a concentration thing. Again, the light bulb itself is retaining that heat.
Right.
The light is going everywhere.
Yeah.
So that light's not getting like contained.
Oh, so when you flick the light on, we're talking about normal light still, it's just all the light or none of the light.
Yeah.
Whereas with the heat,
so a good way to probably explain this is if you have a bare open light bulb, that has a certain amount of brightness when you're looking at it. But if you were to put like essentially a bowl-shaped mirror around it, that directed all the light essentially in one direction and then pointed it, that's really bright.
Yeah.
Because all of the light now is going into the same place. So it gets brighter. But when you don't have that mirror covering it, it's much more dispersed.
Yeah. Well, that's why in a lot of people don't notice this, but in car lights in the back, they have like the light bulb coming out, and then all behind the light bulb, so what's actually touching the car, is mirror.
Just reflectors, yeah.
Because then all the light, like 100% of the light will come out of the light bulb, but obviously some of it will go behind it and it won't be as reflecting.
Which is also why when you're driving up to another car in night, like say a parked car, and your headlights are going on it, the lights at the back of someone else's car, even though they're not on, might seem to like reflect and glow a little bit because that reflection's coming back.
Yeah, that's what they're there for.
When you're looking at colour, that's to do with the absorption of different wavelengths. And you're essentially only seeing the colour that's the colour brackets, plural, that are being reflected and everything else being absorbed. White, pure white being everything that's being reflected. Black, I doubt a lot of people have seen actual black because, say for example, when you're in a pitch dark room, your brain is still almost like making shapes and things out of it because that's what your brain does. There is a substance, if you can look it up if you want, called Vantablack.
I've heard about this.
It's a material made of nanotubes, which basically absorb with 99.7% of all light that hits it, I think. So this thing is so black that it literally becomes basically impossible to discern depth.
I see.
So you can, for example, if someone's wearing some black clothes, you can still see like the shape of, say, their legs. They're wearing some black jeans or trousers or anything. That's their shape is still there because they're not like it's black, but it's not absorbing so much that it's basically devoid of light. But when you're looking at this Vantablack, it's still not entirely, but functionally, as far as our eye can tell, that's devoid of light. So it essentially just looks two-dimensional. You can bend it and shape it however you want. Just look at it and it's like it's two-dimensional.
Oh wow!
Because the light just does not reflect back off of it. We can't perceive the ridges and different shapes on it.
I see.
Because it's not reflecting anything.
Wow. That's impressive. What do they make?
So I am waiting for clothes to come out with that.
They're probably very expensive.
No, it would be very expensive. It's not realistic, but it would be really cool.
So like Vantablack dye.
You wouldn't be able to get a dye of it, I don't think, because of the way that it's made. It's like all nanotubes and stuff, so it wouldn't work. It's not a pigment as such.
So it's in nanotubes. So how does that work then?
I'm not entirely sure. I'm not gonna go into things that I don't know because I don't want to give out wrong information.
Did you hear that, guys? Josh has just ruined the whole podcast. It's going so well. Well, it's pretty much 50 minutes. Do you wanna? I don't know if there's anything you wanna just add to it, or that would be a nice little nugget of an episode. We can figure out what other stuff to do in future episodes and whatnot.
I think I mentioned just quickly to do with things about metals and conducting electricity and stuff because yes, metals conduct electricity. That's all our wiring is like copper and all that sort of thing. But metals obviously aren't exclusively the only conductors of electricity.
Like glass.
Glass is not a conductor of electricity.
There you go. See, I'm telling you. Okay. Obviously, plastic isn't.
No.
Wood
a lot of non-metals aren't.
What non-metals are?
We have a few.
There's flesh that are humans. We're like.
That's because it's a lot of water, and water itself doesn't conduct electricity, because it doesn't have that free electron movement. It's the things that are dissolved in that water, the dissociated ions, so you end up with positive and negative bits. So, for example, you have your salt, your table salt, sodium chloride. If you dissolve that in water, you get sodium ions and chlorine ions.
So when you dissolve things in water, it splits.
Okay. They dissociate. So you have a compound, but they're still reactively to each other, which is why you still form salt when you evaporate the water and not sodium and chlorine. Probably be quite dangerous if it did. But that they're separated from each other within the liquid. And that separation, there's basically things in the water that are holding a charge. The overall charge is neutral, but there are things that are holding different charges within that solution, and that allows the electrons to move by abusing those charge differences.
Okay.
So water itself doesn't conduct electricity, but it's salts that do, and salts aren't metals, but they do contain metals.
To like a much smaller scale.
The same thing happens as well with molten salts when they actually melt. You have extremely high temperatures to do so, but if you had molten table salt, that would conduct electricity.
Oh, right.
There is also the other exception. There are probably more, I'm not aware of them, but graphite. The same thing that is your pencil lead.
Graphite isn't a metal?
No.
What?
Graphite's carbon.
Okay.
It's just carbon. But the way it works is that essentially you have hexagons, linked up to each other. Oh, where's it up the mic again?
We're doing it.
I need to stop using my hands to explain
we're
things.
on point. We're both equally doing it. It's good.
But basically, there's loads of hexagons essentially connected to each other, like how they tessellate. Do you know the word tessellate?
Yeah, it's like
You
a
know,
honeycomb.
Yeah. So you got like a honeycomb. That's a good way of describing it, like a honeycomb of carbon atoms.
Yep.
But like a single layer of atoms.
Right.
And then under that, you've got another layer of exactly the same.
Yep.
But they're not directly bonded between those layers.
Right.
But there is like intermolecular forces that are bonding them. So you have intramolecular forces, much like you might have, say, an intranet at your work or something.
Yeah.
And there's the internet, which is broad and outside.
It's basically inside outside almost,
Yeah.
isn't it? But it just,
So intra
it's like super
is
and supra.
inside, and inter is outside between.
Yeah.
And those, so between the carbon atoms in a layer, you have intramolecular forces because they're the same molecule.
Yep.
But between the layers, you have intermolecular forces holding them together.
It's the inter.
And those intermolecular forces are relatively much weaker than intramolecular forces.
Yeah.
So the reason why your pencil works, essentially, is because you have all those layers, and when you rub your pencil on the paper, the layer rubs off. And the layer rubs off. And the layer rubs off.
Yeah.
Which is the end why your pencil wears down, because you're essentially just like scraping carbon off onto the paper.
Yeah, it's weird. I've done that before in the past. When people write things with pencil, it's like you're wiping. It's like you're wiping like a non-liquid down.
Yeah,
it's quite funny.
Yeah,
to think about.
And it's called a pencil lead. It's not lead. It's carbon. It's not a metal.
Yeah.
But graphite, because of that spacing and the intermolecular forces, and I think because the carbons are only bonded 3 ways.
Right.
Whereas carbon can make 4 bonds.
Right.
It provides an extra avenue for the electricity to flow.
Okay.
So because you have that freedom where the electricity can flow between the layers of the graphite. So if you basically shaved off the end of a pencil and had the open lead over here on the left and on the right, and you had 2 open ends of the lead, you connect those both up and you'd be able to make a circuit with it because the electricity would run through.
Oh, I see. Huh.
Pretty much, as far as I'm aware, pretty much every other non-metal doesn't conduct electricity.
Okay, the last thing I've just thought about to ask is just positive and negative charge. Is that an easy one, or is that...
That's just concentration of electrons.
So we've
talked about concentration.
Briefly explain
that. So essentially, electrons are negatively charged. So if you've got more electrons in one place than another, it's going to be relatively negatively charged.
Right.
So, for example, you rub... So the whole friction can often be used to exchange electrons, and say you're rubbing, say, a balloon against a curtain.
Yeah. And
then you're using it to make your hair stand up on end.
Yeah.
Essentially what you're doing is transferring electrons. I can't remember which. There is an actual specific way which round it is, but I don't remember which.
No problem.
Essentially, electrons are moving from either the balloon or the curtain or material onto the other.
Yep.
So then the other is, one of them is relatively negative, and one of them is relatively positive. Then you move that to somewhere else, and although your hair, say, isn't charged, because still that balloon is negative proportionately, it will then like make your hair stand up. Yeah. Because it's pulling that what's not, your hair isn't positive, but compared to the balloon, say, it is positive.
0 is positive compared to -5, for example.
Yeah.
You know, it's so that's why
it's not positive, but it's still less negative.
Yeah. It's all about that makes sense.
Then we can start using double negatives and stuff, which is great.
Even more confusing.
Language.
With the positive negative charge, I remember asking you this, I think, and me just being confused about it, I was like, what does positive and negative charge mean? And I think looking it up, it doesn't mean anything. It's
relative terms.
There's basically, when you have this sort of thing, because the universe needs balance, one is like plus or 1 or A or whatever, and one is just the opposite. And the easiest way to describe them both is positive and negative. They can be, but they're not, one of them, like electrons, aren't necessarily, it was one of those things where I said, if you swapped everything inverted, So if you made, because electrons are negative, if you made all electrons positive, but you made all what are the
protons?
If you made all protons, which are positive, negative, and you made all the negative ones positive, you just swap them.
There'd be no net change.
Yeah, because it's not about.
Yeah.
It's not that there is a positive and there is a negative. It's that they're just the words we have to use to describe how they kind of work. And one is there's just two of them basically. And the whole balance
it's the semantics of how we describe them, essentially we just use the whole term of positive and negative.
You have
drivers.
to have 10 of one, you have to have 10 of the other. There has to be exact balance between them in the whole universe. It has to be that sort of thing. And that's where it all just boils down to. It's just the balance of it all. So, because that was one of the things that weirded me out. I think I read an article about it or talked to you about it or something, and it was just like, yeah, positive and negative don't actually exist. There's no such thing, but it's just our words we give to it. And that's why I got a little bit confused, I think, because people were always telling me positive and negative. I was like, what do you mean they're positive and negative? What does that mean? It's like, I never explained that in school. It's just, they were just like, that's the way it is. It's like, but that's not working. And then it's like, no, it's not. It's just our name for them. It doesn't.
Yeah.
Ironically, it's relative. But I think we've covered, like, a good amount. Yeah, I think everything really makes sense that I can think of with energy. I mean, this is the second time you explained it to me, and I forgot the first time, so I've no doubt about the next podcast I'll have forgotten this again. But it's all fresh in my mind now. I think this has been a really good first podcast. I think it's been...
This has worked quite well. I'm hoping that I haven't like getting over enthusiastic and basically shouting into the microphone, but there we go.
For a couple of times. I think the viewers will appreciate your enthusiasm. But that's cool. No worries. We'll I'll release this whenever we release it, and we'll try and start figuring out what the next episode's going to be about then, can't we?
Mm-hmm.
Right, thanks for listening, guys. I'll see you later.
Thanks.
Thanks for tuning in, guys. So that was the first episode. I'm not sure when I'm going to release the other ones as of yet, but it will be, fairly sporadically, so you can look forward to them just popping up. And don't forget to, follow us on Instagram, like us on Twitter, subscribe on YouTube and any of the podcast apps that you listen to us on. And, put iTunes reviews up. I do read them. I've actually already got one as of recording this, which made me very happy from someone. 5-star review, getting in there. One step closer to taking over the world. I'm recording this outro of Josh there, and he's just putting funny faces at me. It's making me try hard not to laugh. But just like us on all the social media guys. All the social media things, guys. And I just really appreciate anyone listening to this. Thanks.